What we want to do now is introduce something called the sensible heat factor, and this is an important concept that's used in practice, so it's something that I want you to be aware of. And in practice, it's a little bit different than how we did things from a thermodynamic perspective in terms of thermal purity. They have measurement, practical ways that they do things, and this is one of them. So now let's take this following situation, and I'm going to have cooling going on, and I'll have cooling, and I'm going to have 2000 CFM at 80 degrees Fahrenheit and 67 degrees wet bulb. So sometimes they use a wet bulb temperature. We're going to have liquid come out at 60 degrees Fahrenheit, and what I want here is 58 degrees Fahrenheit and 80% relative humidity. And we'll call this state 1 and state 2. So if I look at that as state 1 and state 2, omega 1 is equal to 0.0112. Specific volume 1 is equal to 13.85. And H1 is equal to 31.6. At 60 degrees Fahrenheit, H is equal to 28 BTUs per pound mass. That's H sub F. So you look that up in the tables. And at state 2, H2 is equal to 22.9, and omega 2 is equal to 0.0082. And again, I can go through and find the mass flow rate, I can find the water, I can find the cooling requirements, and all that sort of stuff. And then we're going to look at how this is drawn on a psychrometric chart in practice. M dot A is equal to 2000 CFM divided by the specific volume, 13.85, and that's equal to 144.4 pounds mass per minute. The mass flow rate of the water is equal to M dot A times omega 1 minus omega 2 is equal to 144.4 times 0.0112 minus 0.0082. So if I do that, I'll find the mass flow rate of the water to be equal to 0.433 pounds mass per minute. And I can find now, if I do a first law on this, I'll find out what the cooling requirements are. So W dot cool is equal to M dot A times H1 minus H2 minus M dot of the water times H sub F. So the cool is equal to 144.4 times H1, 31.6 minus 22.9 minus 0.433 times H sub F, 28. So we end up with the cooling requirements. So we're going to find here 1256.3, that's from the del H term of the air, minus 12.1, which is the contribution for the water. And so this is equal to 1244.2 BTUs per minute. And so it's 6.2 tons. So if I divide this by 200 BTUs per minute per ton, I get 6.2 tons. And what happens in practice, so we have this example. So we had the example, so I have numbers and I'll refer to them. So in practice, HVAC they look at sensible heat and latent heat. And the sensible heat change occurs, so sensible heat change occurs without a change in omega. And obviously the latent heat change, and so this is your delta H. And here we have delta H with omega change. So now let's look and see what that looks like on a psychrometric chart. So what we did is, I didn't go over like this, but here and down and back. We're looking at the system changing from here to here. And when I do that, I can break this into a change of latent heat, which is for the mass flow rate from 1 to A, and a sensible heat change the other way. So Q dot latent is equal to m dot A times H1 minus HA is equal to 144.4 times 31.6 minus 28.6. And so I have Q dot latent is equal to 433.2, and Q dot sensible is m dot A times HA minus H2. And you determine the enthalpies, right? This is how you find the enthalpies. So this is equal to 144.4 times HA 28.6 minus 22.9. So I have that Q dot sensible is equal to 823.1 BTUs per minute. So then the total heat is the sum of the two. Is Q dot sense plus Q dot latent. So I have then Q dot total is equal to 1256.3, and the sensible heat factor, at last, the sensible heat factor is equal to Q dot sensible over Q dot total $823.1 over 1256.3 is equal to 0.655. So that gives us the sensible heat factor that we're interested in finding out about, and this is used in industry practice.